Thank you for having me here today. My name is Kevin Boyd, as was just pointed out, and I'm going to talk to you about light trapping in single crystalline silicon solar cells of micron order thickness. Our work is a collaboration between McMaster University and the University of Toronto, as well as it is Project 10 of the Photovoltaic Innovation Network. Okay, so I'm just going to throw some terminology out there that I'll use during my talk. When I discuss thick silicon, I'm referring to single crystalline silicon wafers that have a thickness of 100 microns or greater. So this is the thickness that is used in traditional single crystalline solar cells in industry. And then when I talk about thin silicon, I'm talking about single crystalline silicon wafers that have a thickness on the order of 10 microns or less. So a bit of an outline for the talk. I'm going to talk about the motivation for using thin silicon for photovoltaic applications. I'm going to talk about the necessity of light trapping in thin silicon. I'm going to talk about inverted pyramid texturing as a solution for light trapping. I'll talk about a novel texturing scheme that we have to create inverted pyramids. And then I'll talk about a novel test platform that we've created to test light trapping in crystalline silicon. That's made of crystalline silicon. So for our motivation, why do we want to use thin crystalline silicon for photovoltaics? Well, first and foremost, cost. So we know that the cost of silicon has dropped over the years, and it's predicted to drop even further. So if we can reduce, silicon's already cheap enough as it is. If we can reduce the thickness of the wafers that we're using for photovoltaics by an order of magnitude, we can draw that cost down even more. Another reason, and this is more of a selling point for silicon in general, is that silicon is abundant and non-toxic. So silicon is the second most abundant element in the Earth's crust. Compare that to other photovoltaic technologies such as cadmium telluride. That's on the other end of the spectrum where tellurium is very, very rare. So we want to use silicon because it's cheap and it's everywhere. So we might as well use it, as well as there's a very mature manufacturing industry behind silicon. Another reason is that thin silicon wafers can be fabricated through a lossless process. So traditional thick wafers are created by sawing from a silicon ingot. The sawing induces losses known as kerf losses, which wastes our valuable silicon. But thin silicon wafers can be fabricated with a process that doesn't waste any silicon. So one way of doing this is proton-induced exfoliation. So protons are embedded into a certain depth in a thick silicon wafer. The protons then turn into hydrogen gas, and when the substrate is heated, the top layer will peel off. So we can continually peel off thin silicon wafers from a thick silicon wafer, conserving silicon in the process. So what are some challenges for using thin silicon wafers for photovoltaics? So the primary challenge is that silicon is a poor absorber of light at very thin wafers. So we have here a plot of the fraction of the AM 1.5 G spectrum absorbed in a particular thickness of silicon. So we can see for traditionally thick wafers that more than 90%, so at 100 here, more than 90% of the AM 1.5 G spectrum can be absorbed in that 100 microns thickness of silicon. When we drop the thickness by an order of magnitude, we lose some absorption. So the absorption, by dropping it by a factor of 10 down to 10 microns of thickness, we end up getting about 68% in absorption. So it's not terrible. Even at 10 microns of thickness, since silicon's still absorbing quite a bit, we could probably achieve a decent cell performance from this thickness. But we do want to make up for the absorption losses, so we need to implement some kind of scheme to enhance absorption. So light trapping is a scheme for doing this. So what light trapping does is it redirects the path of light in a cell. So light will now travel, using a light trapping structure, the light is bent at an angle into the cell. The path length is increased through the cell, and so the photons get absorbed more readily. Light that gets coupled beyond the critical angle in the cell can be completely trapped by total internal reflection. So, how do we trap light in a silicon cell? Inverted pyramid texturing is a very popular method for doing this. So what inverted pyramid textures do is randomize the direction of light in the cell, again, increasing path length like I described in the last slide. Inverted pyramid texturing is featured on the highest efficiency single crystalline silicon devices. So you can see here the inverted pyramids that are featured on the Pearl cell, which we know is the best silicon cell to date. So these feature sizes of the inverted pyramids that are featured on thick silicon wafers are generally several microns large. These feature sizes would be incompatible with a 10 micron thick solar cell or less because the active thickness of the silicon wafer would end up being mostly consumed in the texturing process. What we require are smaller inverted pyramids. Furthermore, when you push the feature sizes of these inverted pyramids down to the wavelength of light, they act as diffraction gratings. So the smaller feature sizes you have, the higher the angle of diffraction. So the higher the angle of light traveling through the cell, the longer its path length will be. It'll be absorbed more readily. So in this study, we've investigated two inverted pyramid textures for silicon. On the left here, we have it's a scanning electron microscope image of 5 micron inverted pyramids fabricated with photolithography. 5 micron refers to the base of the pyramid. On the left here, we have 1.3 micron inverted pyramids fabricated with our novel laser writing process, which I'll describe to you. So due to the fact that the 1.3 micron pyramids are smaller, we expect them to perform better on a solar cell. So how do we make these inverted pyramids? Well, we coat silicon with a thin layer of silicon nitride and then apply laser pulses to the surface. So when the laser fluence is below a catapulting threshold, the dielectric coating simply blisters. Once the laser fluence goes beyond the catapulting threshold, the dielectric coating is ejected and a crater is left behind in the silicon surface. So then we can treat these craters with KOH, or potassium hydroxide, and selectively etch pyramids into the craters. Using this process, we can fabricate very high-quality arrays of inverted pyramids for light trapping. As well, we can selectively pattern the area of our solar cell. That way we can leave room for metal contacts, because you don't want to lay metal contacts down on an inverted pyramid texture. So now that we have these inverted pyramids, we need a thin crystalline silicon platform to test them on. So we've developed a 10 micron thick silicon membrane, single crystalline silicon membrane that's supported by a thick handle wafer. Now this membrane is very well suited for testing light trapping, both optically and electrically. So we start with an SOI wafer, silicon on insulator. So the device layer is 10 microns thick. And then we texture the surface using the process outlined previously. Then we grow a thick thermal oxide on both sides, which will act as a masking step in the later stage. Then, using a custom etching apparatus, we begin to etch through the handle wafer of the silicon, or of the SOI wafer. So we load the sample with the handle wafer upwards into this apparatus and dip it into a solution of KOH. KOH then attacks the handle wafer through the hole in the top there. Now this is where the thermal oxide comes in handy, because we found that we can't leave the membrane inside this apparatus for the whole etch. By the time it gets to the handle wafer, it breaks the membrane. So what we do is we etch partially through the membrane with this apparatus and then remove it and put it into KOH and let it finish the etching. During that stage, the front side would be attacked by KOH, but we have the thermal oxide there to protect the front surface. Once the handle wafer's been removed, then we remove the thermal oxide and the buried oxide using an HF dip. An emitter can then be doped into the front surface, and then we can contact the front and back to turn this into a solar cell. So far we have not done the last two steps here for a textured membrane. We have for an untextured membrane. So we know that we can do it, but due to timing concerns, we haven't gotten this far yet. But we do have a textured membrane. So this is what they look like. I don't know if these pictures come out very well or not, but you can see that it is partially transparent. So this is an picture of an untextured 10 micron membrane. The membrane diameter is about 1 centimeter. And using this process, we can actually fabricate membranes down to 2 microns. So here's, on the left is a picture of a 2 micron membrane. And then on the right, it doesn't look like it came out very well, but I took a picture of my eye through the silicon. So it's quite transparent. Now that we've got our inverted pyramids on a single crystalline architecture, how do we evaluate the light trapping performance of them? Well, quite simply, we can just measure the optical absorption in the membrane. So what we do is we measure the looks like it didn't come out properly. But basically, you shine an incident power on the solar cell, and then you measure the reflected power and the transmitted power. The power absorbed inside the membrane will be the incident power subtracted from the sum of the reflected and transmitted powers. And these measurements can be made using an integrating sphere. And the membrane, you can see, is an excellent test platform for testing light trapping because we have access to the backside, so we can directly measure transmission losses. So here's reflectance data for 5 micron inverted pyramids on a membrane, as well as reflectance data for an untextured membrane. So we can see already that the inverted pyramids are reducing our reflection quite a bit. So they are operating as we would expect them to. Now here's some reflectance data for the 1.3 micron inverted pyramids. At this time, we don't have a textured membrane with 1.3 micron inverted pyramids, but we do have them on a thick silicon wafer. So we compare the 5 micron inverted pyramid reflectance with that on a membrane with that of the 1.3 micron inverted pyramids on a silicon wafer. Now these above 700 nanometers of wavelength, these curves are not directly comparable because we're going to see extra reflection in the membrane due to light being bounced off the back surface. But we can compare them below 700 nanometers, and we can see that using the 1.3 micron inverted pyramids, we're reducing reflection even further. And this is without an anti-reflection coating. Once you put an anti-reflection coating on, we'll get significant more absorption in the silicon membrane. So yeah, in summary, we want to use really thin crystalline silicon for light trapping, for photovoltaics, because it's low cost, we can fabricate it without wasting silicon, and there's potential for high efficiency. So poor absorption in silicon membranes, or poor absorption in thin silicon requires us to implement a light trapping scheme. Standard inverted pyramids are not useful for light trapping, so we use smaller inverted pyramids. And finally, we implemented these inverted pyramid textures onto a light trapping test platform that's 10 microns thick. That can potentially be made thinner. And here's some references, and I'm done.